Hello everyone, my name is Ralph Carter. I'm a Chief Network Solutions Architect with CDI. Today I'm going to be talking about the AWS Gateway Load Balancer with Transient Gateway integration, as well as integration with Palo Alto's, specifically for inbound, outbound, and east to west security. All right, so let's kind of cover that agenda. The agenda is we're going to review objectives of the architecture or of the solution. We're going to review the benefits that this design brings. We're going to discuss the design architecture, kind of talk about the different AWS constructs that are needed to be implemented to be able to support this inbound, outbound, and east to west architecture. And then we're going to also do perform packet walks to kind of explain exactly the per hop behavior and reasoning why these constructs were created or designed in a certain way to kind of make sure that the packets are forwarded to the appliances in a specific manner, right? So I'm confident that after we kind of go through those packet walks, it will explain some of the decision making and some of the reasoning for implementing these AWS constructs during the design architecture. Okay. All right. So let's kind of talk about the objectives of this architecture. The objectives are to block external attackers for inbound security. Where would this apply? So for example, maybe you're hosting some kind of public service. Maybe there's a website or some other application. Maybe DNS as an example, something that's available publicly. So users on the internet or maybe third parties connect to this directly, and you want to be able to control access and make sure that there's nothing malicious going on when they're accessing your services, right? So this is a perfect way to kind of inject a layer 7 next-gen firewall into that communication stream. Okay, so blocking external attackers. Also, blocking data exfiltration. So this is more for outbound use case. So say, for example, you have your internal servers, right? They need to talk to the internet. Maybe they want to do updates. Maybe they're connecting to third parties. Some kind of communication that is initiated from inside outbound, right? You want to be able to see that communication and be able to stop malicious activity in its tracks. And the last use case here is for east to west security. So this is controlling lateral movement, and specifically in the current design that I'm putting together, this is for inter-VPC communication. So for example, maybe you have a production VPC and you have a development VPC, and you have developers connecting to your development VPC, but you want to make sure that they don't just have full reign and be able to connect to the production VPC. You want to have some kind of network perimeter, right? So this solution will allow you to control access between VPCs, okay, that would be sent to a Palo Alto and inspected in this case. All right, so what are the benefits of this architecture? Why do we really care? One of the big benefits here is for the inbound use case, where in the previous implementation with Transient Gateway and for example, the inbound VPC, where you would put a ALB or an NLB in front of the Palo Altos and it would load balance. In that scenario, you would have to always configure source NATing on the firewalls, right? With this new architecture, that goes away. So we don't have to do any source NATing on inbound firewalls. There's really no change to the source or destination stacks. Another big positive here is that there's no more requirement for IPsec in order to be able to load balance traffic to 2 or more firewalls. So in the previous Transient Gateway architecture, you have your VPC attachment, you have your VPN attachment. In order to do equal cost multipath or be able to load balance to 2 or more firewalls, you had to do a VPN. And VPN, obviously, there's some performance penalty there because there's a lot of overhead in the encryption decryption. So service appliances usually struggle with that. So in this scenario, in this architecture, there's no more IPsec. The traffic is delivered securely to the appliance, right, using Geneva encapsulation, and once the firewall receives that packet, you know, the speed, the performance is much better. Also, lower cost alternatives. So now you can start looking at consolidation strategies where you don't need a separate inbound VPC, a separate outbound VPC, a separate east-west VPC. You could kind of consolidate them all and have a single, you know, firewall rule set to manage everything, right? And then you could scale this out if you need to add more bandwidth, as an example. But the goal here is that it could be a lower cost alternative, and you could collapse all your firewalls into a single VPC, you know, made up of a firewall farm. It's very simple to configure, right? So being able to deploy to provide the application to connect to the firewall. You know, it's a very simple service, an endpoint service that would be deployed. You could also deploy a firewall as a service. So for example, if you're an IT administration or an IT team in a company, or you're a third party, you know, support vendor, etc., you can now work with your customers or your different teams and provide them a firewall as a service, right? And there is obviously horizontal scale and fault tolerance with this solution. So these are some of the benefits of the architecture. I'm sure there's other things. The things that I'm hearing more from customers that they're excited about this are the first top two, right? More specifically the performance, right? The no more IPsec required for ECMP load balancing. A lot of our customers are asking about that because they want to be able to load balance traffic and have full active deployments, right? And then the natting also helps that there's no more source NAT. All right, so I'm going to go through the architecture design. I'm going to kind of lay out the different AWS constructs, everything that's really needed to be able to support this architecture. I think after I go through this architecture, it's going to make a lot more sense after we go through the packet walk, because after we go through the packet walk, you'll understand the decisions for, you know, the separation of routing, why we need separate route tables, why we need separate subnets, and all that other stuff, right? So just kind of stay with me here. I'm going to go through the design, and then we'll go through the packet walks after that. All right, so we're going to start off in AWS. We're going to create a security VPC. In this case, I'm using the 10.128.0.0/22 IP block or CIDR that's going to be used for this VPC. And I want to deploy 2 Palo Alto firewalls, okay? Again, these could be BYOLs or these could be marketplace, it doesn't matter, but I want 2. If it was 1 firewall, you're really not gaining the full benefit of this architecture. I mean, you could still, there's still some benefits by doing a single firewall with the gateway load balancer, but you know, you're not really going to realize it unless you kind of do more than 1 firewall. So we're going to make sure that these firewalls are deployed in different availability zones. In this case, I'm using AZ US East 1A and 1B. And I'm going to have to start deploying subnets, right? So the first subnet I would design is a security data subnet, 1 in each AZ. I'm assigning IP addresses of 10.128.0.0 for the first one and 10 for the second one. And this subnet is where one of the interfaces on the Palo Alto is going to connect to. I would kind of consider this a trust subnet, but not necessarily, because this firewall in this particular design is going to work like a one-armed firewall where traffic is going to enter on the same interface and it's going to exit on the same interface. Now, what you could also do is carve up sub-interfaces and then map VPC endpoints to each sub-interface where you can set up different zones, right? But in this case, this is not really a trust interface like you would on in other designs. This is more of like a data transit interface, okay? I'm also going to need to have another interface for my management traffic, right? And other things like internet access. so where my NAT gateway would connect to. So I have a NAT gateway security or subnet, one in each availability zone, using a different IP block, but part of the same CIDR, obviously. This is where my management interface would get deployed into, and this is for things where I'm going to manage the Palo Alto as well as make sure that it gets updated properly, etc., etc. Now, it's also where I'm going to connect my NAT gateway. So in this case, I'm going to have two different NAT gateways, one for each availability zone, and it's going to attach to this subnet. Now, in order to get out to the internet, obviously, you're going to need an internet gateway. So the NAT gateway is not going to do much unless you have an internet gateway. So that is basically planned here. Now, because we're doing the transit gateway, I'm going to need to have transit gateway attachment subnets, right? So, you know, my best practice is to kind of create separate attachment subnets, and I'm going to also create separate, tie them to different routing tables. I'll get into that in a couple seconds. So anyway, I'm going to create separate subnets, 1A and 1B, and these are going to be attached to a transit gateway, and it's going to be a VPC attachment, right? So the transit gateway is going to connect to it, not with VPN, but with VPC attachment, and it's going to connect to these two subnets. Okay, so yeah, so the transit gateway subnets are basically what the transit gateway attaches to, right? I call them the transit gateway attachment subnets. It is a VPC attachment, and we are configuring this in appliance mode so that the traffic can get load balanced properly. So the appliance mode configuration on the transit gateway is not something you could do in the GUI. You have to hit the CLI to do that. As part of my deployment phase in the next part of this video series, I'm going to show you exactly how to do that. All right. So we now need to design the gateway load balancer. So this gateway load balancer is what is going to be responsible to forward packets to the respective Palo Alto firewall. Okay, and this load balancer is going to have not physical interfaces. It looks like physical interfaces. It's going to have its interfaces mapped to each of the data security subnets. Okay, basically on the same subnet as the Palo Alto data interfaces. And we're also going to configure a target group where we're going to specify both of the Palo Altos as targets, and this is going to be an instance-based target, okay? And one of the things about the Palo Alto is we have to make sure that the Palo Alto is configured with the data interface first and then the management after that, and then we could swap the interfaces part of the deployment phase. But anyway, we are going to set the Palo Altos as the targets. It's an instance-based configuration, and the Palo Altos are also being monitored by the gateway load balancer. So there's health monitors that are hitting that data interface. In this case, I'm doing HTTPS, and what you need to do there is on the interface level of the Palo Alto, you would have to set up a management profile, and in that management profile, you would allow HTTPS as an example, right? That will allow the self monitor to kind of keep hitting that firewall to ensure that the firewall is operational, and for the load balancer to be able to forward packets to it as needed. Okay, and the way we're going to get packets to the gateway load balancer is through something called a gateway load balancer endpoint. Okay, so we basically register the service, the endpoint service, and then we deploy these endpoints in various parts of the network. In this case, I'm showing you the use case for outbound and east to west, and for outbound and east to west, I deploy these endpoints within the security VPC. For inbound, it's not really here. Inbound, the endpoint is going to be actually deployed within the application VPC, which I'll show in a couple seconds or a couple minutes. So the gateway load balancing endpoint needs to be part of a subnet. Okay, so in this case, I create a gateway load balancer endpoint 1A and 1B, and each of the respective gateway load balancer endpoints are mapped to the subnet. Now, we're going to talk about the route tables, and this some of the reasoning for why we need these different subnets, and then obviously why we're going to need all these different route tables, because we have to have a routing separation in order to properly, make proper next hop decisions, right? In order to properly steer the packet to the appropriate next hop. Okay. So in this particular case, we're going to create a route table, data 1A and 1B for the security data subnet. Nothing special in this route table. It just has the local route because it's really not doing much, right? The gateway load balancer is going to communicate with the Palo Alto, meaning it's going to send packets to the Palo Alto using Geneva network of Geneva encapsulation. So they're kind of like both on the same subnet. So there's nothing else that really is needed, in that route table, right? So just kind of keep it default. But then for the gateway load balancer endpoint route table, that subnet is going to map to it. In here, we're going to have to get a little bit creative. So what we're going to do is we're going to create a default route that points to the respective NAT gateway, 1A and then 1B on the bottom. And also we need a 10 route that points to the transit gateway. Okay, and once we go through the packet walks, it'll start making sense why these next hops, these routes are created. But just keep this in mind. You're going to configure this routing as a set it and forget it. You're never going to have to come back and modify it. Now, one thing to note here is that if you do have 172, like 16 networks or 192.168 networks, then you're going to also want to add them in this list as well. Okay, I'm just keeping it as 10.0 because that's the only thing I have really in my lab environment here. So I really don't need anything else. I'm also going to create a route table for my security transit gateway, and I'm going to set the default route in this case to the transit gateway. I'm sorry, to the gateway load balancer endpoint 1 and endpoint 2. Okay, so as traffic comes in from the transit gateway into this subnet, and the next hop has to be determined, it's going to forward traffic to the gateway load balancer endpoint directly. Okay, and that's why we're manipulating that. Again, we're going to go through the packet walk in a little bit. And then we're going to need route tables for the NAT gateways. Okay, one for each. And for example, for the first one, we're going to do a default route 0000 via the internet gateway. Okay, and we're going to do a 10 route to go the other way back to the environment, and we're going to do the 10 route /8 via the gateway load balancer endpoint 01 and 02 respectively, depending on which device or NAT device, etc., or what device you're connected to and what the next hop is, right? Now, let's talk about the application VPC. So in this case, I have the demo production VPC. I'm using a different IP block, obviously, right? The 10.128.12.0/24. Now, I'm just using a /24 because this is a demo environment. You're probably not going to want to use a /24 in a real world deployment, in a production deployment. Might be a little too small for scalability reasons. You're probably going to want to do a /22 or maybe a /16, etc., right? So I'm going to also use one availability zone because it really doesn't matter. What I'm configuring here can be replicated across 1, 2, 3, 4 more availability zones within that VPC. It doesn't matter. So what I'm kind of showing you here applies to all of these. So I'm going to create a private subnet. Now the private subnet in this case, my production private, this is where like my, let's say, internal applications reside or are mapped to, maybe my applications, my databases, maybe not devices that are publicly facing, right? Although I can, if I have some kind of proxy like a load balancer in another subnet, but in this case, let's just pretend these devices naturally are not contacted through, through the external, through the internet, for example. Okay, so this is my private subnet. And I'm also using this subnet, just to make it simple, right? I'm using it as my Transient Gateway attachment subnet, where I'm connecting, doing another VPC attachment for the demo production. And then I also have another demo development VPC attachment. It's kind of not showing here because I don't have any more screen real estate. I wanted to kind of show you guys a big, big bird's eye view of this architecture and not kind of flip through slides. So let's just pretend that the demo environment is a replica of the production environment. It's really not going to differ here. And these VPC attachments are mapped to the spokes route table on the Transient Gateway, okay? And one configuration on the spokes route table is that I'm going to have a default route pointing to the security VPC. What you're also going to notice here is that I don't have any other routes for other VPCs because that will defeat the purpose. We want to make sure that when a packet comes in from one VPC, if it's on its way to another VPC or the internet, I want that traffic to go always to the security VPC for inspection, right? That's the east to west use case as an example, or the outbound use case, okay? And the same thing for return traffic in this case, the security VPC will map to the security route table, okay? And in this case, I am propagating routes, right? So the security route table knows about not only the security VPC, right, but also about the production and the development of VPC. So if a packet enters the security route table, it knows exactly how to get to the next hop, okay? And the prod private subnet will also be mapped to its own prod private 1A route table. The only thing we need to configure in this route table is a quad or default route pointing at the Transient Gateway, because we know that the servers in this private network, if it's not talking to anything local to the VPC itself, then send that packet directly to the Transient Gateway, and then let the Transient Gateway forward the packet wherever it needs to go. In this case, it will go to the security appliance, or to the gateway load balancer and be load balancer security appliances. All right, so now let's talk about our inbound use case, right? So in our inbound use case, we're going to have some public servers. These might be servers that are, in a production VPC or in another VPC. It doesn't matter, right? I'm just kind of showing it all in one little location. It's all going to work fine. In this case, I have a production public subnet, and the VMs or actually instances that I put into this subnet are instances that are publicly available. Maybe they're web servers, maybe they're proxy servers, maybe they're load balancers, maybe it's a DNS server, right? Maybe I deploy a DNS server. Obviously, it's going to have a private IP address, but now I can assign an elastic IP address to this DNS server, and with this architecture, I can make sure that even though I assign an elastic IP address directly to the VM, that traffic will get inspected by a service appliance or a Palo Alto firewall in this case, right? That's what this design is offering. So in order to provide the inbound communication, I'm going to need in this case, a demo production internet gateway, which will be bound to the VPC. And I want to be able to redirect traffic to this gateway load balancer. So in order to do that, I'm going to have to spin up another gateway load balancer endpoint. So in this case, I'm going to create a third gateway load balancer endpoint, which is specifically for this availability zone in this production VPC. If I had another availability zone, then I would spin up another gateway load balancer endpoint. And just like the previous in the security VPC, I need to map this gateway load balancer endpoint to this gateway load balancer subnet. Okay. And one thing that I'm doing here, a little creative, is I'm taking advantage of Ingress, VPC Ingress routing, right? So with this, I am creating a separate route table called prod ingress route table, and I'm doing an edge association. So I'm basically associating the IGW to this route table, and the sole purpose of this is so that any traffic that comes from the internet gateway, once it consults this route table, you're going to notice that there's a route there that says 10.128.12.0/26, which is basically the public, the prod public subnet. So any IGW traffic that's going to come in to the prod public, destined for the prod public subnet, will basically be redirected to the GWLB E03, right? That's the gateway load balancer endpoint, instead of going directly. Okay. I'm also going to have a route table for the prod public, and any traffic initiated from the prod public. I'm going to have a default route that points to the gateway load balancer endpoint 03, and I'm going to have a 10 route that points to the transit gateway. Now the 10 route, again, if you have 172 or 192 networks, you're probably going to want to add them there as well. And last but not least, I need to assign the gateway load balancer endpoint subnet to a separate route table. And again, that would be a default route with using the local IGW of the demo production, and the 10 network that would point to the transit gateway. Now, so we're creating all these subnets, and we're creating these route tables, and we're putting all these entries. Again, this is a set it and forget it architecture, but we need to create these different subnets and route tables for next hop separation, right? We need to be able to strategically route the packet to the appropriate next hop. And I'm going to start answering a lot of that, because some people might be wondering, well, wow, this is crazy. Why are we doing all this stuff? So let me go through the packet walks, and then that will start making more sense as to why we need all these entries in here. Okay, but just keep in mind, it's a set it and forget it architecture. It's an active architecture. This is perfect. This is exactly what my customers were definitely looking for. So let's go through the outbound packet walk. Okay, so let's get our packet here. Our packet's going to begin at the prod private 1A. As I mentioned, outbound means, in this case, internal resources would want to communicate to external resources. Outbound meaning using the internet, not east to west, not going to on-prem, although this would fill the same use case, but in this scenario, I'm talking about connecting to either third parties that are using a public IP address, or or maybe I'm going to get a Windows update or a Linux update, or connect to GitHub or whatever, right? So what happens here? So the prod private 1A, internal or private instance on prod private 1A, it's going to consult its routing table on its next hop decision. And it's going to see that the destination is something on the internet, so it's going to use the quad 0 route, the 000 via the transit gateway. So the packet's going to get forwarded into the transit gateway, and it's going to land on the demo production VPC attachment. Well, what happens next? Well, it's going to consult its routing table to determine what its next hop is, and its next hop is a default route via the security VPC attachment, because we need to send it to the security VPC. So we're going to use the default route there. So the packet is then going to be, it's going to go through either the top transit gateway attachment or the bottom transit gateway attachment, right? It's going to share that load here. And then the packet is going to enter on the security VPC on the security transit gateway attachment subnet. And then what is it going to do? It's going to consult that route table, and it's going to notice that there's, how do I get to the internet in this case? Well, I'm going to use the default route. But my default route is pointing at the gateway load balancer endpoint. So if it arrives on the Security Transit Gateway 1A subnet here, it's always going to go to gateway load balancer E01. So it's going to forward it directly to the gateway load balancer endpoint. And the gateway load balancer endpoint, once it arrives on that endpoint, right, it's just a regular endpoint service endpoint. It's going to use a private link connection to the gateway load balancer. Okay, so once you send packets to this endpoint, they're automatically going to get sent over, in this case, to the gateway load balancer. The gateway load balancer now has to make a decision which firewall to send the packet to. And the load balancer has, obviously, a hash algorithm that it's going to use to determine, right? But it's also going to see if the firewall is in an available healthy state, right, through those different monitors that we talked about before. So it's going to pick a firewall, and it's going to forward that packet. Now, the gateway load balancer is going to forward the packet to the Palo Alto on the directly connected subnet, right? Because it has an ENI that's on the same subnet, the security data subnet. And that communication is going to be in, it's going to be actually Geneva encapsulated, right? So the gateway load balancer is going to forward the packet to the Palo Alto, and it's going to be in encapsulated format, okay? So yes, the firewall vendor, the code version has to support Geneva encapsulation. Palo Alto, in this scenario, it is December 2020 where I'm creating this video, and the Palo Alto is running version 10.02 in order to support this configuration. So once the Palo Alto receives the packet, it's going to perform layer 7 inspection. It's going to see if the if the communication is allowed, if there's any malicious intent, if there's any data exfiltration, etc. Right? So the Palo Alto is going to scan that packet, and then it's going to forward it back to the gateway load balancer, right, using that Geneva encapsulation. Once the load balancer receives that packet, it's going to send the packet back to the original endpoint that sent that forwarded that original packet to the load balancer, right? It has this kind of symmetrical, symmetrical return, let's call it, okay? The gateway load balancer endpoint now receives the packet, and it has to do another route table lookup and say, okay, well, how do I get to the internet in this case? Well, guess what? I'm going to now look at my route table, and how do I get to the internet? Oh, I have a quad route 000/0 for the NAT Gateway, because hey, I'm coming from a private IP subnet, and I'm not going to be able to be routed on the internet if I have a private IP, a source IP address, right? So I need to go to a NAT Gateway. So now the packet gets forwarded to the NAT Gateway per the rules of that routing table. Now the NAT Gateway takes that packet, he NATs it, changes the source IP address to an IP address that is routable on the internet, and then the route table on the NAT Gateway gets consulted. In this particular case, how do I get to the internet? Well, I use the default route, the 000, and the next stop is the Internet Gateway. Internet Gateway picks up the packet and forwards it out to cyberspace, right? And eventually that packet returns, right? Because the client, whoever was, the internal server was communicating with, or service that it was communicating with, is going to reply, right? So the reply packet is going to come into the security VPC, because that's where the NAT Gateway, the NAT Gateway owns that IP address, right? So it's going to basically come into that IGW and then up to the NAT Gateway, because that's the true return path. The NAT Gateway then is going to change the header back to the original, and guess what? The route table that he's that he is mapped to is going to be consulted. So now the destination is the prod private IP address, which is in the demo production VPC, and the route table gets consulted. Well, how do I reach the 10 network now? Oh, look, I have a route. It's the 10.0.0.8 via the gateway load balancer endpoint 01. So the packet is going to get forwarded to the original gateway load balancer 01 in the same AZ. The gateway load balancer 01 here is going to forward the packet to the gateway load balancer. Remember, if you send something to the endpoint, it's automatically going to use a private link to the load balancer in here, and the load balancer is going to maintain that session stickiness, and it's going to forward it to the Palo Alto, where the Palo Alto is going to match up the original session, right? You have your TCP, your SYN, SYNAC, ACK, right? All that is kind of SYNAC. That communication is going to get established, right? So that firewall needs to maintain symmetry. So he's going to inspect the packet, and then the Palo is going to forward the packet back to the gateway load balancer. And guess what? The gateway load balancer is going to forward it back to the endpoint because it's going to maintain that traffic symmetry. So now the gateway endpoint receives that packet, and guess what? Well, he's got to consult his routing table because he's got to know how to get to the 10 network. Oh, well, look at that. The route for the 10 network is via the Transit Gateway. So in this particular case, the packet is going to go to the Transit Gateway. But it's going to arrive on the Security VPC route table, right? Because it's kind of just like following its next hop decision making. And the security route table is going to get consulted. Now, the next hop here is a little bit more specific, right? Because we're going to the 10.128.12.64 subnet, whatever. So my next hop here is the 10.128.12.0/24 via the demo production VPC attachment. So the packet will get forwarded directly to the prod private instance. So this, what I just shown you here, is a use case for outbound security. Now, the gateway load balancer can easily forward that packet to the other firewall, but it's all flow based pretty much. Okay, so it's based on a hash. But we could effectively have outbound for all different instances to share, well, the traffic is going to pretty much be shared between one firewall and the other. And if one firewall goes down, well, guess what? The other one takes over and everybody's happy because traffic continues to run. Some sessions would have to be rebuilt, unfortunately, because that's just what happens. These Palo Altos, in this case, do not share session state, but, you know, the world goes on, right? All right, so let's talk about the east to west packet walk in this particular case. So the east to west use case is very, very similar, right? Because we're also going to the security VPC. In this particular case, I have my prod private instance, and the production VPC wants to talk to the development VPC. What is the traffic flow here? So basically, the route table gets consulted. We know that we have a default route for the Transit Gateway. So the packet lands on the demo production VPC attachment. It's going to consult its route table, and it's going to say, well, I'm trying to go to the 10.128.13 network, which is the development instance, right? Because I'm doing an east to west operation. Well, the spokes route table doesn't have an entry for that specifically. It has an entry for the default route, and this is on purpose, right? This is why we want to do this. So it's going to use the default route in order to get to the demo development. But what happens is that packet gets forwarded. Again, it could go to the top Transit Gateway attachment or the bottom Transit Gateway attachment. Doesn't matter. So in this particular case, it's going to go to the bottom Transit Gateway attachment, and then guess what? The routing table gets consulted again. Well, I still need to get to the 10.128.13.0 network, where what's my next hop? Well, it's the gateway load balancer endpoint 02. So the packet gets forwarded directly into the endpoint, which makes its way to the gateway load balancer, and the gateway load balancer Geneva encapsulates the payload to the Palo Alto firewall for inspection. Again, this is an east to west communication. So now the source here is the demo production VPC, the 10.128 64 network, and it's communicating with, you know, the 10.128.13 something network, right? The Palo Alto either allows it or denies it, and then the packet goes back to the gateway load balancer with the Geneva encapsulation. And again, the gateway load balancer is always going to return the packet to the originating endpoint, right? And then guess what? The route table gets consulted again. So the route table in this case would be the gateway load balancer endpoint route table. In this case, we're going to the 10 network, right? We're not going to the internet. We're going back to the 10 network. We're going to the 10.128.13 network. So how do we get there? Well, we follow that 10.0.0.8 route, which is towards the Transit Gateway. We're going to land in on the demo security VPC attachment. So what happens? You guessed it. We're going to consult the route table. Now we can see what's the next hop for the 10.128.13.0. Well, it's the demo development VPC attachment. So the packet pretty much goes to the demo development VPC, right? So this is clearly a very exciting use case where we're able to control communication, and this is low latency stuff we're talking about. Like all these hops that I'm showing, that does not incur any performance penalty. I mean, this is like lightning fast, okay? It's all pretty much software defined behind the scenes with you know, in AWS. But anyway, so that would be the communication pattern, and I'm not going to show you what the return traffic would look like because it's going to take the exact same path through the firewalls to communicate back to the production system here, right? But I'm just showing you the general traffic flow to get to the load balancer and to one or the other firewall. So let's now talk about the inbound packet walk. Now, inbound packet walk, again, I have a public service and I want others to kind of connect to it, and I want to be able to get that traffic to be inspected. So in this case, I have a packet that's originating from the internet. Somebody, you know, wants to connect to our web server. Our web server resides in the prod public 1A subnet here on the demo production, right? This web server has obviously a private IP address, but has an elastic IP address map to it. So traffic is going to come in to this IGW on its way to get to this IP address. And what's going to happen is the route table, the prod ingress route table, is going to get consulted because we're doing VPC ingress routing and we're doing an edge association. So the packet here is going to say, well, how do I get to that prod public? Well, guess what? My next hop is not a local forward. It's my next hop is via the gateway load balancer endpoint 03. So the packet gets forwarded to that endpoint, and through that private link, the packet goes directly to the load balancer, right? That AWS private link. So the gateway load balancer receives it, does its hash, and then forwards the packet to one or the other firewall using Geneva encapsulation. The firewall inspects the packet and then forwards the packet back to the load balancer. Load balancer then returns the packet back to the original endpoint, global load balancing endpoint, not in the local security VPC, but this time in the demo production VPC, right? Because that's where the gateway load balancing endpoint actually resides. So guess what happens? Well, the local routing table gets consulted now because this packet has to exit the subnet, right? So in this case, the destination is the private 10 address, right? The 10 address being via the Transit Gateway. Wait, correction, I'm sorry. It's going to use the local route, right? Because it comes in on the gateway load balancer endpoint, and it's part of that VPC, so it's going to consult the local routing table, in this case, the 10.128.12.0/24, right? So it's going to use the local routing table as a decision to forward that packet to the prod public, okay? So in this particular case, you saw an inbound request okay, get sent to the Palo Alto for inspection, right? In this scenario, I have a web server, and then that web server has an elastic IP address assigned to it, and even in that scenario, I'm able to send that packet to a Palo Alto for inspection. So now this prod public instance has to respond back to the internet. Well, what does it do? Well, it consults its routing table, kind of like what we were talking about. But if you see here, the default route for this gateway, for this next hop, is actually the gateway load balancer endpoint 03. So the packet is going to get forwarded to the gateway load balancer 03. And then over the private link, it's going to get sent over to the gateway load balancer, and then the gateway load balancer is going to forward that packet to that original firewall so that that session kind of stays maintained. Firewall is going to examine it, it's going to return the packet back to the gateway load balancer, and then go back to that gateway load balancer endpoint. Now, the next hop is going to get determined, because at this point we're going back to the internet. Well, guess what? I have a 000 route pointing to the IGW, so the packet gets forwarded to the IGW, right, and then gets sent out. Okay, so then because of that elastic IP address mapping, we're good to go. We can send it out. It gets natted on its way out of the VPC. So pretty much that is the use case. And again, for this prod public subnet, you know, we either place instances onto the subnet with the assumption that we're going to assign an elastic IP address to them, or if we want, for example, other instances to also be available publicly, like for example, if we have instances on the private subnet there that need to be accessed by third parties through the internet, then what we're going to need to do in this case is either put them on the public subnet or put them behind a proxy. So for example, we would put some type of proxy on the public subnet. We could put an ALB load balancer, right? So they could provide load balancing, or actually proxying for HTTP or HTTPS traffic, or we could do a network load balancer and do UDP, TCP, etc. Packets. Oh, actually not. I don't believe UDP. UDP, I think it will not maintain the. It won't maintain this. It will maintain the source IP address, so the packet won't ever return properly. So UDP applications are going to be a little bit tricky. In that particular case, you're going to want to put them onto that public subnet. But if they're TCP applications, we can front them with a load balancer. Maybe you want to allow RDP access from the internet in this particular case, but the endpoint is actually on the private subnet instead of the public subnet. So we can make that happen by fronting it with some kind of load balancer or proxy. But typically, if you're going to want private instances to be available on the internet or accessed separately, then you're going to want to come in through a VPN, like maybe a Zscaler, or with the app connector, or through a Palo Alto VPN service, etc. Right? That's probably the better way to do it. But anyway, that is pretty much it. This is kind of my video. The Gateway Load Balancer was released about 2 weeks ago. I wanted to kind of create a video about the inner workings, at least about how I understand the architecture and the value that I find with it. I think it's a very powerful tool. So I want to thank you guys for watching. Definitely check us out at cdillc.com and also my website techsnips.com. So thank you for your time today.